What's up, everybody? Welcome to another episode of the mini-series EOSIO Architecture Overview. And in this episode, we're going to cover the merger, the relayers, how they set up with the mind readers we've seen in previous videos, and how they all come about to create a highly available setup. Let's start right now. In this episode, we're going to use the whiteboard. And you've noticed I'm not so good at graphs. I'm trying to be better. So we'll make that an exercise. So I'm going to draw here a mind reader. Here, we've got a mind reader and another mind reader just for highly available, okay? And for high availability. In this one, we have node EOS. This is the representation of node EOS. Bear with me. This also is node EOS. And these are connected to the peer-to-peer network everywhere, right? They are just your standard node EOS, and these are two reading nodes that you want to be providing data for the rest of your infrastructure. And you can imagine here we've got other diffuse services like the search live, we've got the search indexer, we'll have, EOSWUS for WebSocket streams, and they all want to be fed with block data. So the first part is mind readers, and they offer a gRPC, right, endpoint. That is the same one we've seen earlier in the previous videos. Let me show you that. This one here. Remember, we're in here proto, and then diffuse bstream v1. Proto is the name of the repository, and bstream.proto. And over here we have, it's the block stream service, gRPC service, in which you request blocks, right, with a burst potentially. And what you get is actually a blockchain agnostic block with the bytes that are not decoded at the level of the mind reader. They're going to propagate, and the subsystems will therefore decode them as EOS block and then understand it. But from this perspective, it's just blocks flowing through. And the next layer we want to go through is the relayers. The relayers are those that are going to enable high HA. If we have a relayer here and a relayer there, they will both together connect to the mind readers here and across like that. So we will have a highly available setup this way. It means if you kill that one, or you kill that one, or whatever, one goes down, it won't disconnect all your subsystems, right? You still have a path for blocks to go through your systems. It also has the benefit of having, for example, this one is in Tokyo, this one USA or something like that. They will also perceive the network differently and bring you faster certain forks or certain blocks that arrive faster. And if you converge those, well, this node here will be able to get the information and pass it through faster, and it's also going to get it and serve your users from the closest location. Now, in this node here, we have, so this is the relayer here, and we have a deduplicator in the form of simply the fork DB, or the forkable that we've seen in previous videos. Check out the video here about bstreams, fork DB, and forkable handler. So when you receive a copy of the block, it's going to be the same block from here, from there, in most situations where you're not in forking situations. And in that case, it's going to be deduplicated, so it's not going to send it over there. Now, another benefit of the topology here is that the relayers act as a fan-out mechanism. We can have more relayers here. And let's say we can easily, the search live, we can have 12 of those, right? We don't want to put too much burden on this one because it's going to saturate his network card or something like that. So we'll have that second, which incurs a small latency, but in different setups, you can put those relayers, for example, on each nodes and have the services running on that node connecting to that relayer. So it's going to be through the Loopback interface, it's going to be pretty fast, and you're still going to have that sort of guarantees of high availability. Now, some very witty persons will say, look, if you have someone is not yet connected here, and some fork happens there, and this guy is fed a fork that this guy is never going to see. So we didn't want that. We wanted to have a solid guarantee that if the whole platform sends you information about a certain block, and that block gets forked out, and you're left sort of dangling, we always want, when you bring those cursors in from the search, we're going to look into that later on, we always want to be able to navigate back out, right? Very important guarantee. If you touch a system, you'll always be able to get back to the longest chain and never miss a beat. So for that, we have another component we call the merger. It's here, little m, and its role is to receive what we'll call one block files. And one block files are produced by the mind readers there, and they're written to some object store, Azure Blob file storage and S3 and Google storage, whatnot, Minio. And they will write one block at a time, tick, tick, tick. Most, depending on the circumstances, most of the time it's going to be when it's real time. And the merge is going to get these things and merge all of the perceived forks into what we'll call here the 100 blocks files, BLK files here. This is a little bit hard to read there. 100, right? 10. And as you recall perhaps in the previous videos, this is what is fed when any system boots. They want to sort of load in their memory 300 blocks or whatever, the last lib segment. They will start from these files and connect also to relayers to sort of very rapidly boot. And these 100 block files, they're executed files. They are the protobuf that we just described in the here, right? At the relayer level, though, they are not decoded. So they're just bytes flowing here, and at some point the services will decode them. They're not decoded for efficiency purposes, so just go on a wire, tack, tack. Okay, but in the merger, we get them, we accumulate them, and we write those 100 block files. And this ensures that any other system could eventually, at least if it wants to, go and fetch the missing block if it hadn't been in memory. And the systems are designed for that. So we give that guarantee. You've seen a view of the network. The platform will ensure you get consistent, reliable access to get out of there, right? Remember those fork situation, tack, tack, tack. You get into a fork. If you were left there, you disconnect. You want to be able to come back and go to the longest chain, right? You were in there, left there. You want to go back to the longest chain. We will always have that segment available for you. Okay, I guess that's clear. At least I've repeated it. Now, let's take a quick look at a non-HA setup. If you don't have a high availability setup, you don't need, if you don't want, you don't need to have multiple mind readers. But in that case, there's also, maybe if you want a small setup, you can have no relayer and just everyone connects directly to the mind reader. And in that case, there's a small flag called mind reader -- mind reader merge and store directly. This does the job of the merger. Instead, it's going to accumulate those 100, and there's only one perceived, network, so it's the one that's under your feet. So it's going to write to the 100 block files itself, and it's going to serve. Because mind you, the relayer's gRPC service is exactly the same as the block stream. It's exactly the same, except it'll present a merged view. So these systems always assume a merged view. This one gives a non-merged view because it's just has less information, but it's the same API. So you can remove the relayer, you can remove the merger, then you have a smaller setup. That's what you'll run when you're on your laptop. And you can, on your laptop, you can also have those 100 block files if you want to test the merger written to disk, just another object store there. So, does that work? Does that make sense? I hope so. Hope you guys enjoy these little, if you have any comments, send them in the channel, Telegram channel. By all means, go and see that diffuse-EOSIO repository and star that so you can inform us that you're active in the space. And yeah, I guess that's it for this video. I'll see you around. Thank you.